So there are some things to note about this. Let's draw a picture graphically over about what the radiation integral, because this is the radiation integral. Really, that's the radiation integral for sources that are in free space. So let's assume that we do have some sources that are in free space. We've got some current density J on this blob of sources. When we're evaluating this integral, I'm going to change colors here. R prime ranges over just this region that contains the source currents. While R is an observation point somewhere else. And take a look at how these two variables show up in this equation. The output is the magnetic vector potential as a function of R. The input is the source current density as a function of R prime. And then there's this term that has both R and R prime in it. And it's the difference between the two positions. There's our R prime terms there, and there's our R terms here. If you are mathematically inclined or you have seen a lot of things, you might recognize this as a Green's function. A Green's function is the name of a type of function that is a solution to differential equations under a specific set of boundary conditions. So this one is the Green's function for free space. No boundaries anywhere in our problem. The waves can just spread out forever. This is the solution that you end up having. Oh, and I have a minus sign missing right there. There we go. That's the right Green's function. But so when we're evaluating this, the bounds of our integral range over the primed coordinates v, which only happen where J exists. So we got a v prime, a v prime. The primed coordinates are the ones where the integral is happening. And every individual location on our source current distribution contributes to the resulting fields at the observation point. Each individual one of those. Because what is an integral other than a sum of infinitesimally small parts? Each individual one of these points on the current distribution, on the source distribution, adds up at the observation point, and the superposition of all of those individual contributions is the total field that you observe. And that leads to some really interesting consequences, which we will begin to talk about in our next couple of videos.